We are live.
Okay, great. Well, hello, those of you who are watching, and welcome back, those of you who also tuned in last week. So this is the second installment in these kind of live research sessions that Carlos and I have been doing, working on this project that was, I think, initially called Infracalculus. I think as of last week, we kind of both agreed that we slightly prefer the name Infrageometry, because it's sort of it more clearly conveys that what we're trying to do is sort of is somehow develop a formalism that in some way generalizes and goes below the sort of the standard formalism of continuum geometry. So last week we had a particularly exciting inaugural stream where I think we figured out a bunch of stuff, at least sort of somewhat provisionally. We threw some ideas around. We got quite excited by one or two discoveries. I think Carlos is going to tell us that at least one of those discoveries, or one of those pieces of excitement, may have been a little bit premature, but we'll see what we can do this week to rectify that. But so I think the plan. I mean, Carlos put together a nice agenda just before the stream, but I think the basic plan would be we'll start off by just kind of recapping more or less what it was that we covered and what we speculated last time. I particularly want to try and nail down some formalizations of a few of the core definitions. I think Carlos mentioned a couple of them in his agenda, things like, directional derivatives, covariant derivatives, bundles, sections, fields, etc. These are all concepts that we were kind of throwing around last week. And I think we have more or less the same intuitive picture of what they mean in the context of graphs and hypergraphs, but it'd be nice to kind of to nail that down a bit more precisely. And then at some point, I think we want to go, and this is where probably Carlos will take over a bit more. We want to go into more detail in relation to things like derivations, the Leibniz rule, potential sort of discrete Lie algebraic structure, things like that. Okay, so with that, let me see if I can share my screen. Get a brief glance at my Twitter. Okay, so this is the notebook that I think we prepared last week. This is mostly a brainstorming notebook. And so I think at least the first part of this stream, what I want to do is focus on trying to take a bunch of the ideas that we brainstormed and see if we can inject a little bit greater, a little bit more rigor, a little bit more formalism in sort of what we were doing. So maybe, again, I'm open to Carlos's suggestions here, but maybe the thing we can start with is the basic notions of kind of metrics, connections, metric compatibility, covariant differentiation, etc. that we kind of began our proceedings with last week. So if we, what should I call this? I don't know, towards a formalization of infrageometry. To make it clear that we are past the brainstorming stage. But let's do infracalculus. I'll have to change the name of this at some point. Formalization 1 or something. Okay, so metrics and connections. So I guess maybe I should. Okay. So, all right. I think last time we agreed that we both thought that a kind of a reasonable definition of a provisional, and I just want to make absolutely clear again that everything we're talking about here is still speculative. I mean, although we're in a sense we're trying to formalize these speculations precisely so that we can test whether or not they're reasonable. So we're not claiming any of this is final yet. But I think we kind of agreed that a good provisional definition of a metric would be a kind of an underlying undirected graph structure. And then the idea would be that the connection is then some directed graph that gets generated from that from that undirected graph. Or a metric connection would be a directed graph that gets generated from that undirected graph structure. And then if you have more general kind of affine connections that are not necessarily metric compatible, those are just directed graphs that don't necessarily reflect some underlying undirected graph structure. I don't know, Carlos, does that sound reasonable?
Yeah, that sounds reasonable. What I would suggest maybe at this stage is to just as a preliminary point, should we agree on the notion that a set of points, a discrete finite set, is going to be the analog of the sort of intrinsic manifold points? And because in a way, at least in the traditional presentation of differential geometry, you would have, at least intrinsic differential geometry, you would have this sort of manifold set with structure on top, and sort of metric being some further structure on top. And I think last time we were in agreement that this is something we need to sort of come back to and be confident about. But last week we were in agreement that a set of vertices is going to be somewhat analog to having just the set of points of the manifold, and the structures on top of it will represent
Right.
connectivity. I mean, it's kind of strange because it's not quite fully analogous in a way, because in a way your connectivity structure. But at any rate, I wanted to have a bit of a discussion on that specific topic of are vertex sets sort of analogous to just point sets of a manifold, or
Right.
do we have more and things like that?
Yeah. Okay. So maybe we can. Okay. That's a good question. That's a good point to clarify. Okay. So in Riemannian geometry, when we speak of a Riemannian manifold, this is very ponderous text. I'm probably not going to be this ponderous in everything else. When we speak of a Riemannian manifold as an ordered pair, M comma G, in what sense can we think of M as being like the vertex set and G as being like the edge set? So because typically, so M we think of as being a set of points, but it's not just a set of points, right? It's a set of points plus this local homeomorphism information. And then G, so if you just consider M as a set, then I think it is effectively the vertex set, right?
Yeah.
And if we just consider G as like a set, then it is effectively the edge set, I think. I don't know, what?
Yeah, I mean, I had this intuition from last week, and I've been sort of pondering about this for the last few days, and I do have this idea that vertex sets should be similar to point sets. I mean, you do have, if you have a manifold, a conventional smooth manifold, you still have the point set that is a, just ordinary set theoretic collection of things that if you actually forget the smooth structure, just becomes a set, right? So in a way, I feel like a vertex set or a graph in which you forget the edge set should probably be similar to that. And one can imagine, for example, hyperbolic space and I don't know, the real plane. These are two non-compact two-dimensional manifolds, right? Real manifolds. So in a way, so you can find a one-to-one mapping between them. So in a way, you have a bijection of sets between them. The whole point is that they are not isometric, right? You don't find an isometry between them. But as sets, the point set of both hyperbolic space, hyperbolic plane, or the plane, or the Euclidean plane, they are the same, right? They are, so in some sense the same base set is sort of being used into different geometric ways, right? So similarly, you could have the same vertex set that is endowed with different edge structures on top, so that you have different geometries effectively on the same base set, right? I think that's the analogy I have in mind. That's why
Sure.
I think it makes sense, but I might be wrong. I don't know.
No, I'm completely with you on that. So I guess the way I would think about it in light of what we were discussing last week is that, so just the manifold, just the M that's the vertex set plus essentially local directed edge information, right? So so it's the point set plus information that allows you to map a point to its tangent space. Then the G, the metric, is then the thing that gives you the kind of the more global undirected graph structure.
Yeah, I'm not sure about that. I mean, that sounds roughly like what I think should be, but I feel like the term I had in mind these days was that vertex set is like point sets, and edge sets or edge structure is like connectivity structure. And by connectivity, I mean it in a fairly broad sense, so that you can induce something like topology on your vertex set, because obviously vertex set doesn't know anything. I mean, of course you can always do the canonical, everything goes with everything kind of topology, but
and in a trivial sense, right? We know that all graphs are topological spaces precisely for that reason, right? The vertex set is a point set. The edge set induces a neighborhood structure.
Sure, exactly. Yeah.
Okay, so maybe I guess maybe the point you're making is it's worth us just noting that down, right? So vertex set of a graph, point set of a topological space. I'll use.
Yeah,
and then
I think that's a fair, yeah.
Edge set of a graph, kind of neighborhood structure of a topological space. Connectivity.
And it might be, and to build on your point, it might be that by the discrete nature of edges or graphs, you actually have more, and you have because we've seen that an undirected graph structure in a vertex set effectively gives you a distance notion, and it gives you, by projecting down to the induced directed graph from the undirected graph, gives you a sense of connection, and it also gives you a sense of angle as a result, and all these notions that are sort of for free once you assume a particular undirected graph structure in a vertex set. I think that might be, so what is in the screen right now is absolutely true, I agree, but I think it might be quite a lot more, that if you just assume a graph structure, you have for free something similar to a metric structure.
Absolutely. So I think the point we made last week was that graphs are naturally metric measure spaces.
Yeah.
They can be made into topological spaces. So because of combinatorial metric plus geodesic Hall volume measure.
Yeah.
They can be made into topological spaces by forgetting certain details of the structure. Something. And yeah, I guess the underlying point is exactly as you say, because we're dealing with countable sets. Whereas ordinarily, with an uncountable set, if you want to induce a notion of metric or a notion of, you have to impose a metric structure, you have to impose a measure on top of it. The point is that with countable sets, you have the cardinality construction, which, although for continuous sets that cardinality is too coarse, right? It doesn't have any discriminating power. For countable sets, it's actually fine. It has a lot of discriminating power.
Yeah.
And so we can use the cardinality of the edge set the cardinality of the set of minimal set of edges that you need to traverse between two vertices. That gives us a metric. And the cardinality of the set of vertices that you can reach, within distance n, that gives us a volume measure, and that wouldn't work in a continuous setting because as I say, the cardinality criterion is way too coarse. But in a countable discrete setting, it works just fine.
Yeah.
So discreteness means that we can exploit cardinality to give us a metric and a measure. Whereas in continuous spaces, cardinality is too coarse a condition. Something like that. Okay. Carlos's video is turned off.
Oh, sorry.
Sorry?
I think I mispressed.
Oh, okay. Okay, I hope everything's okay. All right. Okay. Do you think there's anything else sort of on the more foundational level that we need to clarify?
This is something that I want to focus on later on, but there is so if we want to talk about bundles and sections and all these kinds of business, I feel like the tangent bundle, in my opinion, the tangent bundle gives you a sort of a model of what a bundle should be like. And I think that last time we had a fairly good idea of what a tangent bundle was. But the problem here is that there seems to be a bit of a clash or a bit of a collapse of what in differential geometry are distinct and generally unrelated or independent notions to be sort of dependent here. So what I'm saying is, last time we said, okay, sort of a rudimentary definition of a tangent space at a point would be the collection of outward directed edges from that vertex, right?
Right.
So that seems very intuitive. I've seen a paper from last week, since last week, where they define tangent spaces as the formal vector spaces generated by such directed edges, which I don't quite like because it's kind of a cop out of discreteness.
Right, exactly. The whole point is we want a model of the vectors. We don't want to kind of import, the added structure of linear algebra on top of it. We want to kind of somehow build that up.
Exactly. Yeah. We want, or in some sense, we want the discrete analog that, in some sense, will be a limit, or will recover things in the limit or something like that. Because
yeah.
Anyway, what I'm seeing here is perhaps similar to what happens when you do classic differential geometry, where a lot of notions are tied to the fact that you are in a Euclidean space, and you're sort of explicitly using the Euclidean structure, even if you don't realize. So what I mean is that what determines what vertices are adjacent to a given vertex is some graph structure that you're imposing on your vertices, right? So, and that's, if we're saying that is naturally a metric measure structure, then it's also directly giving us a sense of tangent bundle or tangent vectors and things like that. So that's why I said that the edge set of the graph is the connectivity of the space, because connectivity means it's meant in a very broad sense, where you're collapsing things like path connectivity, you're collapsing things like neighborhood connectivity, you're collapsing all these notions, right? Like measure, where you can use the cardinality measure and all these kinds of things, right? I mean, so I don't know if, so I'm not saying this is a problem or anything, I'm just saying that a graph structure and a vertex set seems to be many different things if just looked from the right angle in the same.
Right, but I, in a sense, I think this is why it's worth us clarifying again the distinction between the undirected metric structure and the directed connection structure.
Sure.
Because in a sense, the topological point you're making about connectivity is really about undirected edges.
Sure.
Whereas the kind of differential geometric point that you're making in relation to tangent bundles is really about directed edges.
Yes.
And so I think you're probably still right. I think it's probably still correct that we are collapsing several different notions together. Like, as you say, that various different notions of connectivity. It's not clear that they are that they can be. I mean, I don't know. We should actually work this out. I'm sure someone has. This has definitely been investigated. I just don't know what the answer is. Like, which, if you have a graph and you consider a graph as a topological space, presumably there is a minimum level in the hierarchy of separation axioms that you have to exist at. Like, I'm fairly sure a graph has to at least be a Hausdorff space. And so naturally there are certain kind of discriminations at lower levels that we won't be able to make. It's worth us nailing that down at some point. I agree.
No, I think it's I agree on that, but I think it's also at the level of I'm not seeing this as a problem at all. I'm just thinking that the discrete structure, and again, this might connect to the point that we want to investigate later on of higher order structures. What do those correspond to? Because obviously, we're thinking of pairwise connectivity structures here, which obviously are going to directly involve paths. Because that's kind of the whole game in differential geometry. When you begin with tangent vectors, is the whole story about paths.
Right.
And so it makes sense that our first approach is with a graph structure, because that's the most natural, basic reduction, sort of finitary reduction of pairwise connectivity. So I don't think this is a problem at all. I just think that especially for people who are familiar with differential geometry, or like myself, like having a correspondence where you say, oh, this undirected graph corresponds to a metric, and you're expecting to say, well, then, okay, what is the connection? Actually, the connection is induced directly from the same information. It's not the same formal object, because the connection might be the directed graph that is induced by the length one paths that can be that can be traversed in this undirected graph, right? It might be that that's the definition of your connection in this context, and it might be that a tangent space is just the length one paths, the collection of length one paths that you can define from any vertex, right? So it might be that definitions are just a matter of choice of where you place your your focus, but the formal object in the background might be unique. It might be that an undirected graphic structure is enough to get all these notions that classically are unrelated, like a metric structure and a tangent and a tangent bundle structure. These things are disconnected. There's no
except I'm not entirely sure that I agree with that assessment.
Okay, so I want to know. Yeah.
But I mean, I'm not dogmatic about this, but it's more like, okay, so for instance, in some sense, we'll write these definitions down in a second to hopefully make this a bit more clear. But if we say, okay, the metric is an undirected graph, the connection is a directed graph, it's not necessarily the case that the directed graph that you construct for the connection was obtained by essentially taking an undirected metric and kind of directifying it, so to speak. That's what we were doing last week.
Yeah.
But we don't necessarily have to do that. We could just pick some arbitrary directed graph and we just say, okay, well, this doesn't have a corresponding undirected graph structure.
Correct.
So that would be more like something, an affine connection that is not necessarily metric compatible. So it's true that once you have an undirected graph, okay, there's a unique directed graph structure that where path lengths are symmetric, and in which therefore, as you say, the tangent spaces are just given by collections of length one paths emanating from a single point. But the same is true in Riemannian geometry, right? That we know that there is a unique metric compatible, for any Riemannian or semi-Riemannian metric, there is a unique metric compatible torsion-free connection, which is Levi-Civita.
Yeah.
I don't view what we're doing as being fundamentally that different from that.
Oh yeah.
We're saying that
absolutely
we could define all these different components independently. Of course, we could have directed graph structures that don't have corresponding undirected graph analogs. Yeah. But we're choosing not to do that because we kind of we want to exploit, I don't know what we should call the analog of the fundamental theorem of Riemannian geometry. The fundamental theorem of infrageometry or something, which is that there is some kind of uniqueness condition to this construction.
Absolutely. No, I think that as far as the fundamental theorem of Riemannian geometry is concerned, I think that's clear, and I think the analog really is that you have your connection induced, your directed graph induced by an undirected graph, and all that stuff. I think that's clear. My concern is not so much because those are structures that are in classical differential geometry. Those are given by the fact that you are in an Euclidean space, or at least in an embedded manifold into an Euclidean space. But in modern sort of intrinsic differential geometry, those pieces of data are independent. They have to be provided in addition to a smooth structure, right? So my concern here is that the only natural and sort of sane definition that I see for something like a tangent space seems to be indistinguishable from that of some subset of the elements that define a connection, right? In the sense that if you want to have this notion that there is such thing as a space of connected points, right? Which otherwise I don't know why we call it a space if there's no some sense of connectivity between them. Just as a side note, I hate it when people just call sets spaces just because you have many things they call them spaces. Like, why would you use that word if there's no sense of space, right? If there's a sense of space, it means like something like what you just drew, right? Like there's a sense of connectivity and proximity and direction and things like that, and you can traverse and sort of navigate the space in a structured way. It's not the same to go from one point to another in any random way, right? Or at least not in general. And so my intuition is that in the typical differential geometry story, you have space with that sort of basic connectivity, which you normally think of as your manifold with a smooth structure or the Atlas structure, whatever it is. And then out of that, you can naturally define things like curves and things like functions. And then out of that, you naturally have things like the tangent bundle, the cotangent bundle, and directional derivatives, and all that stuff. All those notions are completely independent from things like metric structures, right? Or connections or anything like that. So
I see.
my concern is more in that sort of, bits of information in standard differential geometry, where you have smooth structure gets you for free all this bundle, tangent, cotangent, and tensorial sort of bundles information. And then when you supply things like a metric structure or a geodesic structure or connection, a fine connection or metric compatible or not, and all these things, then you get further structure. And that's the usual game of differential geometry. Is okay, you have a smooth structure and you sprinkle things on top to give it more rigidity in a way, right?
Right. So might a way to think about it be that, in a sense, the details, this sort of hierarchical construction that we outlined last week, and that we'll kind of be recapitulating here, in a sense, is assuming a model, some kind of model space. Maybe it's not entirely clear what the model space is.
Right.
But we know is not max. So in other words, so the construction is not maximally general from the point of view of kind of modern differential geometry.
Yeah.
Okay, so that's an interesting question. I mean, that's okay. That's questions to discuss. What is the model space that we are assuming in these constructions?
Or is there a need for one? I mean, because
right. So, and is there a need for one? I.e., can we make this construction strictly more general?
Because the direct analogy, I think the most direct analogy for something like a model space in this context would be things like very specific kinds of graphs. So things like sequences, which in a way are like paths, and so if you have a path a path is effectively a choice of sequence of vertices which are unordered to begin with, right? So you want to make your definitions in a way independent of labeling, independent of sequential labeling, and if your definitions are algorithmic in nature, finite algorithm defines whatever measure or cardinality based measure on your thing. You want your things to be sort of combinatorially invariant in some sense.
Right. So this is a point that, for viewers' sake, this is a point that Carlos made in a meeting that unfortunately was not recorded, but which we should record. We should record this point now. So Carlos made this point, which I very much like, which I may butcher. So correct me if I'm wrong. But so that sort of covariance in differential geometry / mathematical physics, I guess, is really some analog of the statement that an algorithmic construction on hypergraphs should be invariant under sort of re-indexing of vertices and edges. Is that a fair?
Yeah, that would be a good summary. Yeah.
Yeah. So the idea being that I guess that you have a construction like, for instance, this volume construction where you look at all distance n paths emanating from a single point, and you look at the counting measure of that subgraph. So that construction, at some level, doesn't care about how you label the edges and how you label the vertices. So we can say that it's in some way covariant. Whereas it may be the case that, for instance, there were features of the constructions we were dealing with last week, like the angle construction, where we were looking at kind of we were investigating edges emanating from a single point that were and kind of grouping them pairwise. And so the particular, and then we were assigning a number with each such pair. So the particular sequence of those numbers depends on the order in which we group the pairings. And so that sequence of numbers, although the set of numbers is invariant under reindexing, the sequence of numbers would not be invariant. So that would be an example of a non-covariant construction. So I think that's a very important point to do.
Yeah, but I think it's similar to, in that example you gave, it's similar to the notion that if you have vectors in a metric manifold, you can assign angles to pairs of vectors, but you cannot. But if you have three vectors, you can say what the pairwise angles are, but there's no way to tell that one comes before the other, right? Like it's
right.
They might all be equal, and one is. They have some real values. There are some bounded real values, but you could order them in a way because they are measuring, they are valued in an order set, but there's no sense in which they have a sequential they have a sequential order, right? Like they just exist, and yeah.
So if we say now, okay, so here's a random directed graph, and so the claim is that this is like an affine connection. So so this is our point set, and this is the affine connection. And so then, okay, in a case like this is an affine connection, but the claim would be that it is not a metric connection, because there is no undirected graph which for which the graph distances are the same as for this directed graph, precisely because there are directed edges that don't have a corresponding symmetric counterpart. Yep. So the distance from this point to this point is 1, but the distance from this point to this point is I suspect infinity.
Yeah.
I can't validate that immediately by eye, but I think it must be.
Yeah, I think it is. Yeah.
So there is no undirected graph where the distance function is compatible with this directed graph structure. So in other words, in differential geometric terms, I think the conjecture would be that corresponds to the statement that this is an affine connection, but it is not compatible with any metric. So in other words, so this connection induces a notion of covariant derivative, but there is no metric tensor whose covariant derivative vanishes under this definition.
Yeah.
Does that sound about right?
Yeah, that sounds right. I think my earlier concern was, I guess, the notion of manifold in a way. I mean, this might be perfect. This is actually an exciting prospect now that I'm thinking about it. Is that the notion of manifold is somehow, how to say, sort of vacuous at this point. The notion of intrinsic manifold itself is at this point kind of vacuous, because you have the ability to discretely encode things like what we in differential geometry call structures of manifolds, but we don't have, as of yet, I don't see a clear definition of this would be the exact analog of a manifold structure and only a manifold structure on this set of vertices. It feels more like, okay, so this directed graph could be a connection, and that might be that's it. I mean, you have a connection structure between a discrete set of points, and it might well be that in taking limits and doing some kind of statistical averaging or whatever it is, it might be that we actually end up with something like topological manifolds or whatever. But it might be also exciting. That might be that we have a means of generating. So if you take the rings of functions on these spaces, or the rings of, or the algebras of derivations, or whatever it is, some algebraic counterparts of these objects, it might be that you end up on, non-commutative rings or some specific non-trivial algebras that are more exotic than just commutative rings, which is the case with manifolds, right?
Mm-hmm. Right.
So, yeah.
Right. Absolutely. Okay, so then next step would be to say, so a metric connection, a metric compatible affine connection is one in which there exists a corresponding undirected graph on the same point set, on the same vertex set, I guess, with the same graph distance function, i.e. the directed graph structure can be sort of freely generated from the undirected graph structure. Is that, I don't know, is that clear enough? That may not be very clear. So we're basically saying we take something like this, and then so this is the metric, corresponding metric connection. be that.
Yep.
And so we should also say, in principle, as with the affine connection, these directed edges can be weighted.
Mm-hmm.
And so I guess that leads us on to so the case of a torsion connection, a torsion or torsion-free connection. A torsion connection is a directed graph structure, is a weighted directed graph structure in which the weighted graph distance function is non-symmetric. So we could do, what am I up to now? Graph 4. So we do directed graph that, and then I'll say, so weighted graph 4, and we'll say graph 4 edge weight goes to hash arrows random real 1 mapped over edge list of graph 4, edge labels, edge weight. Okay, so now if we select, so actually, that's embarrassing. I don't immediately know this. How one obtains the weighted graph distance. There may just be a function for that. We can just try it. So I actually don't know whether this works or not. Let's give it a go. Yeah, okay, perfect, it works. Whereas if I did just graph 4, this should just be an integer. Yeah, okay, perfect. All right, so if I say graph distance, so if I pick 2 random vertices, oops. Vertex 2. Vertex 2. Vertex 1. Yeah, okay, so there we go. So the distance function is asymmetric because in this particular case, our connection happened to be torsion. Whereas the kind of the default choice of connection induced from a metric would be torsion-free. And so, as we were kind of discussing before, fundamental theorem of Riemannian, I'll say infrageometry, would be the statement that there is a unique, I guess maybe we should say up to a multiplicative constant. There is a unique directed graph structure there is a unique weighted directed graph structure whose graph distance function for any weighted undirected graph, there is a unique weighted directed graph structure whose graph distance function matches that of the weighted undirected graph.
Yeah.
This directed graph structure, this weighted directed graph structure, is the analog of the torsion-free Levi-Civita connection, I guess, something like that.
Yeah, and I think the fundamental fact that is in the background of this theorem, so to speak, is, I think it's something quite fundamental about hypergraphic structures, which is this dependence on edge symmetry or edge structure and sort of the combinatorial nature of edges, right? Because, it so happens that when you have a binary connection, there's no ambiguity if you say A and B are connected symmetrically. There's no ambiguity that you can say, well, A can be connected to B or B can be connected to A. So if I choose my sequences, that's going to be, a given. I can do that. Um, so in a way, because undirected connection is the least structured of connections that you can imagine. So there's two ways, right? You can always, so if you have a very ordered connection, say you have a list of, or a cyclic list, or whatever, a collection of bags in a list and then in a tuple or whatever it is. It is easy to say, well, I'm gonna take all these elements, I'm just gonna project it down, and I'm gonna put them into a bag. And so you can always, from a highly structured edge, you can always project down to an unordered, undirected edge of the corresponding order. And similarly, if you have an unordered edge to begin with, you can sort of build up partial structures on sort of directed structures on those, right? I think the fact that this is unique in the case of pairwise connections is just the size of the combinatorics. It's kind of an accident of the combinatorics that there's only two species of pairwise edges, right?
Right. Okay. So let's go with Carlos claims. So which I think is quite cool. All right. So let's see. I'm gonna try and restate this claim in my own words, and you tell me if it's a fair characterization. So fundamental theorem of again, I'll put this in inverted commas. Fundamental theorem of Riemannian infrageometry is a consequence of, states a relationship between directed and undirected graph structures in the arity 2 case. This is a consequence, I guess, of the pigeonhole principle or some other basic combinatorial fact that is peculiar to arity 2.
Yeah.
Is that sort of the idea?
Yeah, I would say so. Because when you go higher, you lose uniqueness, and you don't lose the fact that it's given, but you lose uniqueness. You lose the fact that there's only one hypergraph associated.
Uniqueness of the Levi-Civita connection is lost for higher arity hypergraphs.
Yeah, something like that.
That sounds right. That sounds right. Okay, cool. So we have torsion-free connections, fundamental theorem from Riemannian geometry. Okay, so maybe we should move to let's recap tangent spaces and tangent bundles.
Mm-hmm.
And possibly vector fields.
Yeah.
Okay, so tangent space. You had a nice phrasing of it that I liked. So tangent space, the tangent space at a point is a set of distance 1 paths in the directed graph, distance 1 directed paths emanating from a vertex.
Yeah.
I guess. So let's go again to okay, if we bring back our metric connection, which is, let's just generate one. Directed graph 10, 20. And so we choose a random vertex. And we say, okay, so I'm going to show, okay, so what we actually want is the neighborhood graph 5, vertex 1. That's going to show everything. So what do we actually, we want vertex outcome. Yes. Okay. And then then we say directed edge vertex comma hash mapped over that, and then we just say highlight graph in graph 5, or so we can do style directed red thick or something.
Yep. That's good.
And we do style vertex green. Okay, so we pick a point and we get the tangent space.
Yep. Yeah,
Okay.
that looks intuitively very good. I think it might be worth making a note here. Something that just occurred to me. So how about, because this formulation in terms of distance one directed paths, right?
Yeah. There's no particular reason for it to be distance 1, right?
That's exactly what I was gonna say. Yes.
Yeah.
So I was thinking maybe it makes sense to have something like, from a vertex you naturally have a set of paths that are graded by distance, right?
Is the center directed path graded by distance emanating from a vertex? So let's say here we'll do.
Yeah, I'm not sure that should be the tangent space of the point. I'm just saying that that's a structure. Because I mean, okay, in standard differential geometry, tangent space is a construction from a space of incident curves on a point, right? You're doing this quotient thing, and this beautiful construction, if you like, the sort of more geometrical construction of the tangent space. Something similar in this context would be. This is actually interesting. Okay, so let's try to actually mimic the definition of tangent space instead of it looking intuitive to our eyes, right? Because obviously it looks very nice and point and arrows, and that's how you draw it, right? But imagine, okay, let me think for a second. Okay, so if we actually were to mirror the definition of the geometric definition, the curve-based definition of tangent space, in differential geometry, what you need is you pick a point, you have a set of curves that are incident on that point, or that through that point, which is easy enough, right? These are the set of all possible paths that go through that point, and then
Right.
you want to establish a condition of tangency between them, right? That's the main. That's why it's called the tangent space in a way, right? So you want to determine a condition of tangency between them. Now, of course, tangency is going to be strange because so tangency is going to be an equivalence relation between curves that go through a point. So let me just say paths from now on. So so the question is, what would be a natural discrete graphic analog of tangency of curves? It would have to be something like, these are not necessarily identical curves that have some feature that makes them tangential, and I imagine that there's only one thing to exploit, which is the graded structure of the set of all curves, right? Because the set of all paths through a vertex in the graph is a set, okay, and it has a graded structure, right? So I don't think there's much more, because in the case of differential geometry, you have the model space to define the tangency relation, and you effectively use an affine space or a vector space to define tangency. In here, we don't have the notion of model space, but we do have this notion of a graded set of paths. So I don't know. I mean, intuitively, it feels like two tangent paths would point to the same target vertex outwards from the vertex that we're looking at. But that might just, and that recovers the intuitive picture of the tangent space.
Right.
But I'm not sure if there's a more sophisticated definition that is sort of lurking in the background.
So we could do collection of tangent curves.
Yeah.
So we could try and simulate that. So if we took, so we take, let's again do vertex 1, vertex 2, and we say, so find shortest path. Well, I just want to say find path, graph 5, vertex 1, vertex 2, all. That hasn't really worked. Wait, how do I find all paths? I thought it was something like that. Oh, do I have to say, wait, k-spec all? Infinity. Yeah, of course. Okay. Right. Okay. So we do something like that. That may be too many. I don't know. Maybe we're always going to get a lot. Oh my God. Okay. And is this going to be useful at all if I show this? So if I show graph 5, join style vertex 1 red. Oh no, let's do green and blue something. Vertex 2 blue and style. No, we want to do a join of that with style. Oh no, we don't need to do a join, I think. Oh, maybe we do. Yeah, we do. So what I actually want, subgraph, graph 5 hash mapped over curves. Something like that. Except we don't actually want the symmetric version, we want the asymmetric version.
Yeah, I'm just thinking about this, and I think in the interest of concreteness and best use of time, I think it might be it might actually be better to stick with the intuitive picture of the tangent space for now, because
sure.
It does make sense to. I mean, there is a clear analog in which the equivalence, the equivalence class of tangent paths through a vertex is precisely the edge that is pointing outwards in a particular direction.
Right. I mean, so look, here's kind of my view on it. So in the limit, if we want this to approach differential geometry in some appropriate infinite limit, then the cardinality of the tangent space should go to infinity.
Sure.
Right? At the very least. But right now, with distance 1 paths, that's only going to happen if the outcome, if the out degree of every vertex goes to infinity. One way to ensure that you can have an infinite size tangent space in the limit without having to have unbounded vertex degree would be to say allow for path length that are unbounded. And so then effectively you're taking two limits. You're taking one limit as the graph becomes infinitely large, and another limit as the distance becomes infinitely large. And as long as the first limit is kept strictly below, as long as the distance limit is kept strictly below the graph size limit, then that's still a sensible notion. Okay, but so I mean we can just do an example of that, right? We could say so. We could look at the distance 1 case, we can look at the distance 2 case.
I'm just thinking that you might have, as tangent spaces, you might have this graded. So I mean, these graded sets of paths that this is just given. It's just a feature of how you can move around your manifold. It's almost like saying that's the possibility of dynamics in a sense. That's or the possibility of kinematics on on your space. If you want to sort of call back to a physicsy language, it's like the possibility of like basic kinematics is this idea that you can walk on your space and you can move in your space. So at any given point you have this graded set of paths, and you can certainly, especially if you're dealing with weighted directed edges and things like that, you can have this notion of a quotient, kind of a, how to say, it's the usual, you have a graded thing, you can sort of find the sort of I don't know, homological version of it, which is just basically quotienting. So and these would be things like, you want curves that pass by the same vertex and stay, and within, how would you describe it? It's like they stay within the same grade. Yeah, it's something to do with bounding the values of. It's like you have your travel distance, like, which is the basically the count of vertices, and then you have the weight of your edges, and so you can define some kind of bounds for these things, and that's sort of how you would in practice recover limits if you were to do sort of something more like calculus. But again, this feels rather sophisticated at this point, because it would give this finitary but generally very complicated combinatorial structure for each point, and the whole goal of defining something like a tangent space is that, in my opinion, is that it should allow us to construct something that is very much like a tangent bundle, right? And the sections of which are things like vector fields, which should be equivalent to something like derivations. So, in my opinion, this whole business of tangent space should be justified only if we get an effective implementation of derivations, and we see something like a Lie algebra or an analog of a Lie algebra somewhere. I mean, to me, that would be the only use of all this stuff, because doing paths on a graph is nothing new. I mean, we're not going to reinvent sort of like graph theory here to just, to me, it's what is the clever construction that directly takes you to something that looks like a tangent bundle, which, or in more sort of fancy terms, to a Lie algebroid in this discrete context. So I wouldn't dismiss the intuitive definition just yet, because the alternative feels quite convoluted.
Right. Wait. Okay, so if I do that style directly, that. What am I doing wrong?
The age-old feeling.
I don't know. If I can't make this work, as you say, in the interest of time, we should move on. But just quickly. There we go. Okay.
Right.
So that would be the distance 2 case. I don't know if there's a way I can render that makes it a little bit clearer what's actually going on, but hopefully that's reasonable enough. It's like, okay, this is, we're now looking at all distance two paths rather than all distance one paths. And as you say, we can just consider the tangent space to be the graded set of such paths.
By the way, something's missing, I think, right?
It's
not terribly important, but
where?
So
you mean like is it say this path?
So you could take the first arrow on the left, that one, and then you can take that edge that goes upwards, right?
Mm-hmm.
And that would be a distance to path.
That's true. Yeah, because I've only found. Okay, right. So we actually want find path.
And it's not terribly important. It's just illustration.
No. That's fair. So I think we actually want something like that. Okay, I'm going to try that, and if it doesn't work, we'll move on. This is horrible code, of course. It doesn't work. What did I do wrong? Yeah. Okay. Whatever. This requires more work, but I can do this offline. This is not.
Sure.
This is not super important.
Just to summarize on tangent space, and tell me what you think about this. But
Sure.
As I was saying, to me that any definition is only as good as it brings us closer. I mean, as far as it brings us closer to something that is recognizably a tangent bundle.
No, absolutely. No, I think we all agree on that.
Okay.
And I agree that the end goal is we want some kind of Lie algebraic structure here, right?
Yeah,
that's kind of
something like that. Yeah. And yeah. So that's why last time I was sort of trying to shortcut to to derivations of functions, because it does seem to be the case that if you have a vertex set, you automatically, or a graph or whatever data structure, it does seem to be the case that defining functions and those things is absolutely trivial. I mean, you just have an assignment of values, of sort of some kind of field valued functions on your set. So it's not sophisticated at all. And I mean, you end up with a commutative ring out of that just by construction. And it is the case that commutative rings have derivations, and I imagine. Yeah, I like to say that this is probably a theorem that I should know by heart, but I don't think I ever found it. But it is probably true, and I can check this quickly, that if you have a field other than of characteristic 0, something like reals or complex or whatever, and you have a finite set, right? You can have the call the field f. You can have the f valued functions on that set. That's a commutative ring by construction, by pointwise definition.
Right.
That commutative ring has a Lie algebra of derivations, like any ring. That Lie algebra is 0.
Mm-hmm.
That should be the case, because geometrically what you're doing is basically a discrete manifold, sort of a zero-dimensional manifold, and that's the statement that the tangent bundle of a point manifold, like a discrete manifold, is 0. It's just the 0 vector space everywhere, right?
Mm-hmm.
So that's kind of an invitation, I would say, to consider other fields. I mean, fields of other than characteristic 0.
Right.
Like F2 that we considered last week. But it would also be but that's just a very blunt. Yeah, that's a definition of derivations that effectively doesn't know anything about the connectivity structure of the manifold or the graph. Okay, so while you do this, I'm going to check on that.
Yeah, please. Sorry. Okay, so that I claim is a tangent bundle in association form. So we're mapping from. So we have a. No, wait, no, this is bad. The association in the wrong place. Okay, so that I claim is a tangent bundle because what we're doing is we're producing an association which for every vertex maps it to its tangent space, and so the overall association acts like a kind of disjoint union of those tangent spaces. And so if I now take that, say normal tangent bundle, I can do graph 6. No, let's see, highlight graph 6. And at each point, I just want to do last normal. Okay, so now this is every style. No, that doesn't work. But okay, so that's every tangent space highlighted in a different color, although of course there are many overlaps, so it doesn't really make a lot of sense, but that's, I don't know, that's the best way I can think of right now to visualize what it is that we're doing. But yeah, so the underlying point is we can just, once we've got a notion of tangent space, we can just take a disjoint union in the usual way.
Yeah.
And so then the notion of a let's see, so a smooth section of this tangent once we have a tangent bundle, a smooth section of it is just, I think, is literally just a choice function, right?
Yep.
A smooth section is just we just choose an element from every tangent space.
Exactly.
So smooth section of tangent bundles, or smooth sections of tangent bundle. A smooth section of a tangent bundle is a choice function defined over the discrete tangent bundle, i.e. a choice of distinguished tangent vector at each point. So we take the tangent bundle and we say, okay, so for every element of this tangent bundle, we take last / that, we map random choice over that, and then we can just say, so that's going to be a smooth, that's a randomly chosen smooth section, and then we can just say highlight graph 6 style smooth section directive red thick, and that should be a vector field, which I think it is.
Mm-hmm. That looks like a vector field indeed.
Yeah. Okay. So I mean, this is I don't know. I at least think this is a very nice intuition for what a section is.
Sure. I'm completely on board with this intuition.
Cool. Okay. Did you get a chance to check the theorem?
Not yet. So that should be true. I'm not very. I mean, it's kind of a very trivial. It's a very trivial result. I mean, it's like saying, there's nothing wrong with zero-dimensional manifolds, right? Like they work like any other kind of manifold. But zero-dimensional manifolds are collections of disjoint points, right?
Right.
And so you have functions defined on them, right? So that smooth functions on these things are basically just maps from a finite set into your field, right? And so like in any other, like for any other manifold, you have that the space of functions or the set of functions becomes a ring, right? It's a commutative algebra, commutative R algebra, whatever, and that thing has a set of derivations which geometrically correspond to the sections of the tangent bundle, right?
Right.
So the theorem is basically stating that if you have a ring that erases in such way, right, which is you give me a finite set which I interpret as a manifold, it's a smooth manifold, which I can, and you define the derivations over the ring of functions of that manifold. That's a Lie algebra. That's a natural Lie algebra that you can construct, right? It's the derivations, right. and it corresponds to the derivative, and it's in the theorem, the fundamental theorem of differential geometry tells you that the derivations of your functions on your space are isomorphic to the sections of the tangent bundle of that space, right?
Right.
Whatever the notions of those things are in each context, right?
Mm-hmm.
So in this context, we know that because the geometry tells us that these are pointed spaces, so they have no tangent bundle, they have no tangent space. You know that the derivations are zero. So, but zero is a perfectly fine Lie algebra. It's just a very boring one.
Right.
So that's why I'm stating this just to motivate doing something a little bit more creative. Sure. Because if you have a set of vertices, as I said, I'm just going to rephrase what I just said for the audience mostly, but if you have a set of vertices, you could just take the set of vertices and say, I'm going to define functions on them. And that set of all functions on vertices is a ring. And as a ring, as any other commutative ring, it has a derivation Lie algebra associated to it. But because it's a finite set, the derivation Lie algebra is going to be zero. If your field is something like the reals or the complex numbers or something like that, right? So the R derivations and the C derivations and the characteristic zero derivations basically are going to be zero. So you need to do something a bit more interesting. So you could just simply value your things over another field, and I'm pretty sure that you will get non-zero derivation algebras. But I think what is interesting is what we tried to do last week, which is the part that I have to sort of retract and walk back, which I said that there's a Lie bracket on those things, on the finite difference derivatives that we defined last week. There isn't, but there's something that is not too dissimilar to a Lie bracket, and it is kind of enticing to say, maybe that's pointing to something interesting. But yeah, it's different. I don't know what should be the criterion. I'm a bit undecided as to what the criterion should be for the condition that you call something of, the tangent bundle or the sections of the tangent bundle, something like. Because it is immediately obvious to me that is a perfectly fine definition for a vector field, what we have there. Mm-hmm. What I would love to, and it's perfectly natural to me to think that functions should be defined as just valuations on a field on the vertices, right? That seems perfectly natural. So the question is. And it's also perfectly natural that if you have a directed edge between two vertices, there's a completely natural construction of taking the difference, taking just finite difference. That's what a field is for, in a way, right?
Right.
So the finite difference algebra that you get, so it turns out that let me call them, we should probably invent a name for those things. But there's so much terminology about difference, differential, derivative, and so on.
Right.
So, but whatever, the finite differential of a function, right, defined with respect to some direction, which is some vector field. It's of course again a function. It's a well-defined function. So you do have and it's a linear map in any reasonable, because obviously taking difference is linear. So you're gonna get a linear map. So you have a linear map from functions to functions. With respect to addition, it's linear, and with respect to product, it satisfies this quasi-Leibniz identity, which I find quite interesting because it could just be nasty with respect to Leibniz, with respect to product, but instead of being just being nasty and not satisfying any particular property, it satisfies clearly Leibniz plus an additional sort of quadratic term, right? To me, that's interesting. That's quite evocative. That's something going on that is relevant. And that extra term in if you are in the continuous case, that's the term that you can actually cancel out, because you as you take your parameter to 0, that will have a term linear in the parameter that you are making arbitrarily small. So that will be killed off, right? But because we're not taking any limits or anything like that, that term remains. But it's nonetheless kind of quite manageable, right? It's not that, you can't say anything, there's some long expression that depends on the cardinality of your graph. No, nothing like that. It's just that you have Leibniz plus quadratic term of derivatives, right? Like it's not crazy. I mean, it's literally almost the next step more complicated than just Leibniz. It's not hugely complicated.
Okay, maybe this is a ridiculous relation or connection, so to speak, to make.
Uh-huh.
I'm almost reminded of the transformation law for objects in jet bundles, right? So like, if you look at the transformation law, the Christoffel symbols, right? They transform as functions on jet bundles. So what that means is that they satisfy the ordinary tensor transformation law plus some quadratic derivative term, which is the thing that means that they don't transform as tensors under arbitrary diffeomorphisms, only under linear coordinate transformations. I wonder if it's a sort of formally analogous thing that what we've got. In other words, that the structure we're dealing with here is to ordinary Lie algebras what jet bundles are to ordinary tangent bundles, or something like that. I don't know. Maybe that may be a ridiculous claim. I'm just
no. It's interesting. It might be, but if it is, my intuition is it breaks down somehow, because these things are meant to be vector fields, right? So basically what you want to establish is that, as I said in the first live stream, algebra is probably going to be some kind of guide that will tell us, you're probably in the right paths towards the definition of sort of discrete differential geometry. And remember, I think the title for our live stream, beyond discrete and continuous. I want to emphasize this because this might be an unnecessarily philosophical point at this moment in the live stream, but but to me it's actually relevant that our definitions, or at least in my opinion, or in my view, at first order approximation to this problem, our definitions should be independent of whether we want to do some kind of continuous limit in the end. Yep. Right? They should be sort of self consistent and sort of self-justifying, right? Like you should have a theory that, as we claimed in the title, beyond discrete and continuous, that doesn't really care whether you choose to work with, let's take a torus with this vector field, blah, 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 with some sort of continuous data, or you decide to say, well, actually, I'm going to take this graph that captures these features that are sufficient to model this and this and that, right? Because the way I say it is that, when you do differential geometry, there's an infinite amount of information in a manifold, right? Because there's infinite, the cardinality of the manifold, all the objects are infinitary, right? Like there's all over, all kind of huge cardinalities, thrown around. clearly we don't compute with that information, right? We compute with finitary bits of information from those manifolds, right? Like our, the algebras, the way that we encode the properties and the objects that we select or we sort of single out on our manifold and things like that. These are always finite, right? Like we're counting singularities, or we are finding invariant vector fields and bases for spaces, and it's always finitary. We're always sort of working in this finitary regime, and my view is that I have the hope, or I have the, I don't know, intuition, exciting sort of a thought that it might be enough to have discrete models to begin with that actually operate for the same, or effectively operate to compute and to be useful for the same kinds of problems without having to use this infinitary machinery beneath it, right? And again,
right.
And just to refer to a question in the live stream earlier, this is not a claim about the nature of the universe being discrete, or I'm not making any sort of deep assertion about the ontology of physical objects or anything like that. This is simply to say that it's an observation that mathematics on infinitary objects is necessarily finitary when we do it. Like when we interface with it, we are always interfacing with some finitary constructions and finitary arguments. And by that I mean the literal interface, not the things that we say we are referring to. Obviously you can refer to infinite processes and infinite sets and all that kind of stuff, but the actual interface you're using, sort of the symbol, the formal language and so on, this will always be finitary. So my view is that manifold theory, because of all these ideas that we've presented in the last couple live streams, last week and today, it's looking to me like we can capture a great deal, if not everything. I mean, who knows? We can capture a great deal of the computational machinery of differential geometry in a finitary discrete mathematical context. In this sort of hypergraphic constructions and graphs and all the business that we're doing here. So.
So let me just produce some visualization of the finite difference construction that you're referring to.
Yeah, that would be great. Yeah.
So, by the way, I don't know if you know. So this I think now should be correct. This is
yes, that looks.
I think
yeah.
This is the distance 2 version.
Yeah.
But okay. So if we say, what do we want? We want vertex weight, arrow, hash, random real 1 or something.
Maybe, I don't know, it would be a bit noisy to just do it with integers.
We could do it with integers. I don't know, we could do random integers between 1 and 100 or something. Does that look okay?
Yeah, it's probably much more pleasing on the eye.
Yeah, no, that's fair. That's fair. Okay, so then so in that case, so we take, well, hang on, maybe what I should do is actually have a vertex weights. Weighted graph 7, and so then we want to say I just select 2 random vertices. And I take, so make this into an association, then I should just be able to say association of that vertex 2 minus vertex 1, and we can visualize that, right? So we can just say highlight graph, weighted graph 7, and we can see
what I would say is that we probably need, because this is just taking 2, Did it happen to be adjacent by coincidence, or is that
That happened to be adjacent by coincidence. Yeah.
okay? Because I was gonna say, if
Yeah,
they're
yeah,
just
no,
random,
that's true. That's
yeah.
true. In general, they won't be. So actually, what I should do is vertex one is that, and vertex two should be random choice of the vertex out component
Yes.
of vertex 1, comma 1. Okay, so then it just selected itself.
Yeah.
All right, there we go. Another example.
Okay,
Cool.
that's great. Yeah, that looks very good. Yeah.
Okay, so that would be that's the analog of directional derivative.
Yes.
Maybe.
I would say
and
yeah,
then,
maybe. And honestly, I don't see another way. I mean, if we agree that that's there's basically two choices. We go for the lean intuitive definition of tangent vectors, which is just outwards directed edges, and then this is the definition of a directional derivative, and then the definition of a derivation would be instead of just specifying, well, because in this case you specified a pair that was connected, right?
right.
But the idea is if you have a vector field, you can do that construction at every single point, right? And so
Right.
from a function which is a vertex association, you get another function just by computing that difference at every single point, right?
Mhm.
So the idea is your set of functions is some ring, and you are defining something that we're calling whatever discrete derivations or whatever, the derivation, whatever. We give it some sort of fancy name.
Right.
And yeah, and they satisfy something like a Leibniz algebra property. But there are two open questions. There's one, what the hell is that relation? I mean, what can we make something of that? And second, and most importantly, can you define some sort of algebraic structure on them? So, for example, the commutator of d derivations in this sense are not, the commutator of two d derivations is not a d derivation.
Right.
This I checked. In general, that's not the case.
Are there cases in which it is?
I don't know if by choosing specific fields, like finite fields, you're gonna have something that possibly, but in general they are not. And I don't think the F2 case helped in proving anything. Yeah, because these things are
Okay, so if we take, I'm going back to real numbers now because we will be potentially dividing through by things. So it's unfortunately we have to deal with a certain amount of ugliness. Vertex 1, 1. So our directional derivative would just be what we did before. So we say association vertex weights vertex 1 minus, or vertex 2, I don't know, minus association vertex weights vertex 1. But then the covariant derivative would be something like, again, maybe this divided by the edge weight of directed edge vertex 1, vertex 2. Right? So we have some kind of construction that takes a directional derivative and kind of makes it respect the underlying connection, or something of that nature.
Yeah, that's something I was going to comment at the beginning when we gave real weights to a general connection. I'm not entirely convinced what would be the. Because I guess, I mean, wouldn't it just be? Because weight is just So did you just divide by the weight? Is that what you did?
I divided by the weight of the edge. Yeah.
Yeah, that sounds intuitively right. I agree.
But
I mean, I just don't. Because that feels like a very continuous thing to do.
mm-hmm.
In a way. It's like if I'm thinking of that weight as the distance along that edge, right?
Right.
Which before it was just normalized to 1, and now it's some real. It's like, sure, the rate of change is going to be that difference over the weight of the.
I mean, we can go back to integers if you think that makes it cleaner.
So it's not a matter. No, it's not so much the problem with.
No, I appreciate what you're saying. Like somehow philosophically, it feels less discrete to do it this way.
Yeah, I'm just. Because the question is the weight of an edge sort of qualifying the distance of what?
I think that was the idea, right? When we computed weighted distances up here.
Definitely there. Yes, I agree.
For affine connections.
That's why I meant that it sounds intuitively correct. Like if we agree that can effectively model proximity, right? It's like adding, in a way that's right. That's probably and that's actually very interesting because actually a real weighted graph seems to me much closer to what I was saying earlier, that you might not need to deal with the infinitary information that a manifold carries, right? Like it's probably enough that you can capture. Well, I'm sure it's very close to what you've been doing with gravitas and all these computations, right? You have some finitary model that nonetheless is valued over something that has high precision, or something that is sort of potentially taking values ranging over something that could be considered as continuous, but in computational terms it is bounded, it is finite,
right?
But it captures whatever is relevant, or you hope that it captures whatever is relevant for a specific situation, because of you might, like, I can imagine looking at this picture on the screen right now. I can imagine that's some manifold, like that they can travel in, and I see a lot of homology, and those are the paths that are sort of the homotopy equivalent paths that you can take on a manifold, and
right.
But you want to keep something like, okay, there's a geodesic distance of there's some you point your manifold with some scatter of points, and then you take some minimum distance paths between those points, right? Obviously those things are going to know about the homology of the manifold and whatnot, so that's encoded in the topology of the network, but at the same time you can weight them so that you remember the distance that you had in your actual Riemannian manifold, right? Is this something
right.
do you think of this similarly, or?
Yeah, no, more or less. And I think, I mean, that's one of the things I'm quite excited about as a possible offshoot of this program, is investigations of, I guess, what we might call kind of semi-continuous, or semi-real geometry, right? It's like there are many, as you kind of alluded to, right? There are many ways that you can be continuous, and whereas traditional differential geometry is considered the case where the model structure is, everything is uncountable, all the quantities are continuous, all the quantities are real numbers, etc. in principle, there's no reason why you can't kind of have a bit more fine-grained control. You could imagine having a completely discrete
Yeah.
combinatorial underlying model structure, but where your distances are real numbers.
Yeah.
And so you get some kind of like, I don't know what the right term is, but semi-continuous geometry.
Yeah, semi-continuous sounds good. Yeah.
Yeah. I guess you could, and equivalently, you could have the case where actually, the model structure is a manifold, but where you're somehow discretizing distances and measures in some fancy way. I don't exactly know how that would work, but you could imagine doing something similar. And so one of the possible offshoots, I guess, of this infrageometry program is that it allows us to look at not just these extremal cases of fully discrete and fully continuous, but some of these sort of interesting intermediate cases where some aspects are continuous, some aspects are discrete.
Yeah, no, I completely agree, and I think that is justifying the beyond discrete and continuous sort of tagline that we chose.
Absolutely. Okay, there's a lot more to discuss, but just so unfortunately, I'm very happy to reschedule another stream. I think Carlos, you can't do next Tuesday, is that right?
Next Tuesday, I'm not available at this time exactly,
yeah.
But we could do Wednesday, for example.
Yeah. So it's just unfortunate because I do actually have a hard stop at in 14 minutes at the 2 hour mark. But so okay, this is I think useful. But so in terms of what we should do with the remaining time, maybe I don't know. We can. There's obviously more to discuss here, but maybe we could turn over and you could fill us in a little bit on the Lie algebra and derivation side of.
We could do that, or we could think about the higher order stuff.
Oh, okay, yeah, sure.
Because
sure.
I think that's because the Lie algebra part is just for the benefit of the audience. I don't know if you can possibly copy and paste the image that I put on the Discord. I don't know if you have it available.
I don't have my Discord open, but I can open it.
Because if you can just for the record and the people watching, if they see what we're calling quasi Leibniz.
Remind me, where did you post this?
In the internal one. So that one, and it should be just there. The
right.
one the one at the bottom. So
this one.
This one. Yeah.
Okay.
Yeah.
Let's
grab copy
that.
image.
So, yeah.
And I think you can just copy it there. Yeah. So the summary is, if you do the construction that is on top of this, what Jonathan just did with the discrete example of taking a finite difference, then you can very clearly define what I call the discrete derivative, right? Or a discrete differentiation, or a D derivative, let's call it for short, which is doing this construction of finite difference between all the. So you take a vector field that specifies a directed edge on each vertex, and you take the value of the function on that vertex and the value on the vertex that that edge is pointing to, and then you take the finite difference, and maybe you divide by the weight or something if there's something involved, whatever. And the point is that construction gives you a map from functions to functions. That's clear. It is linear. That's clear because it's just defined as the difference. So there's nothing impedes the linearity. But when that construction, that D there is D with respect to some vector field, but they just omit the vector field information, the interaction with the product of functions, which is what you would expect to be something like a Leibniz rule, like vector fields in continuous geometry, you actually get this formula, which is what we're calling the quasi Leibniz rule, which is Leibniz rule plus a quadratic term, which again, if you were in the case of continuous geometry, all these things will be up to a limit where some parameter is becoming arbitrarily small, because you're taking sort of like an instantaneous limit where you're comparing things arbitrarily close. And the first two terms will be unaccompanied by any parameter. They will just be finite quantities that will remain in the limit. And the d.d term, df.df term, quadratic in d term in the end, will carry some, I think, linear or quadratic term in the parameter. And that would obviously go to zero in the limit. So, but we are not in the limit. We are in a finitary context, and so this is exactly what we have to work with. This is the mathematical structure that if you look at a graph and you want you do this intuitive definition of function and intuitive definition of tangent vectors and vector fields and so on. This is the natural notion of this sort of discrete differential or discrete directional derivative, and this is the natural axiom that these things satisfy. So the open question is, can you find? So first of all, this is not Lie algebra. I mean, that's something that it's not obvious. You have to check. If you take the commutator of these things, they do not close under commutator, right? I mean, it's a long computation, but it's just not. It's not very. It's not very evocative to go over it. So these are not closed under commutator bracket. So they are not a Lie algebra per se. But the question is, can you define a bracket on these things? So you can basically modify the commutator somehow, so that this becomes some kind of algebra, some kind of Leibniz algebra or whatever. And my suspicion is that you probably can, but this is a non-trivial thing to do. I mean, this is just hardcore algebra exercise to do here. And so I will work on this sometime during the next few days until the next live stream. Hopefully by the time of the next live stream, I'll have a much more final sort of answer on these sort of animals that we've encountered. Because the summary is, this thing appear naturally. They are novel, I think, mathematically. So it's exciting. I mean, I think this is always an exciting pattern, right? Like you have a clear intuition. We have all these constructions of metrics and connections and tangent spaces, tangent vectors, and so on. And then you do the direct analog of a definition of a directional derivative, and you end up with something that is just a deformation of a Leibniz rule. I think that's a very good sign. I mean, I think I have to sort of correct and retract my statement from last week, which was that the derivations literally satisfy Leibniz. In this case, they satisfy this modified Leibniz, which in my opinion just makes for a rich mathematical problem, and one that hopefully will teach us something, and and maybe these are algebras that belong to some larger category where you can see the algebras as well in some way, and so maybe we can learn something. So next week or next time we meet, I will have a more final say on this and more definitive sort of statement about, can you find some bracket, or is there an obvious way to not do this, or is there any abstraction or anything like that. But that's basically the summary of it. I don't think there's much more to be discussed. I mean, at a later point I can go over the details of how you get this rule, because how you get that rule is actually not super direct. I mean, you have to do some quote unquote clever tricks. I mean, it's not super clever, but it is not like a 2-line proof that you just get that rule. You have to sort of manipulate things a little bit cleverly. So that at a different point I can go over that once I have a more final information. But for now, I think we can use this final 7 minutes or something to speculate a little bit on what higher order hypergraphs might be encoding geometrically.
Yeah, no, sounds good. Okay, so let's maybe go back through this and figure out, okay, so what things change when we go to higher arity. So first thing, notion of directed versus undirected, that obviously becomes more subtle.
Yes. So I would say the main. So I propose to do this example of ternary, just because it's the next step and it's easy.
Yeah.
So if instead of an undirected pairwise graph, you have an undirected 3-way graph, right? What I would say changes is that you're effectively defining a distance for 3 points, right? So there's no fundamental notion of distance, pairwise distance, right? But now you have something that requires 3 points in space, and it gives you a number out of it, right? So the immediate meaning, you can imagine that this is, I mean, yeah, it's like, this is a relation, this is a spatial relation. So can you? I guess you need to load the Packlet if you want to visualize it, right? Just in case we want.
Yes, actually, do you have it loaded?
I have it loaded, but do you want to try if it works for you? Because that would be a good test actually.
Okay, then tell me. I don't think I've ever used it on. Oh, no, I certainly haven't used it on this machine. How do I
Okay,
do it?
so just it's just yeah, pipe install. Let me get you the code quickly. Oops, where is that? Let me quickly get you. I just copy pasted. Yeah, so Packlet install. So I'll just paste it on the Zoom
Yeah.
chat. Oops, for some reason I can't. Oh, it was just laggy.
Okay.
So you think it's an error? Interesting. And then now you have to load it.
So is that Packlet? How do I do that?
The code is again just
Sorry,
with the yeah. I'll send you the code with the two. Just that.
Yeah. Okay. Sure.
So you can just take that list over there
Mm-hmm.
and just wrap it on hypergraph. That should work.
Okay.
Okay, because it shows some duplicates and it does a weird thing. So maybe try not. Can you quickly just delete one time?
So you mean hyper edges that have the same vertex
Yeah.
multiple times?
Yeah.
Yeah. Okay. So let's say select of those tuples.
Be a quick way. Yeah, that's.
I guess something like that. I don't know.
Ooh, still there's something. Yeah.
Oh.
And yeah, I mean that's certainly a ternary hypergraph. So yeah, maybe a bit overcrowded for the illustration, but I think
Let's remove some edges.
yeah,
maybe.
that's better. Yeah. So anyway, so just for illustration, that's basically giving you sort of the basic feature of 3 points in space, which you could imagine is like some kind of neighborhood property, right? Where it's like those 3 are in the vicinity of each other, right? It's kind of interesting to think about how could that be the case without the pairwise vicinities being the case. So in itself, that sort of a homology of arity is interesting, but yeah. So the reason why I wanted to bring this up is that in the pairwise case, you have the notion of path as the leading tool to probe your space, right? Like you're saying, okay, you have this, and then you can define paths as the sequences, and these things are naturally composable, and you can and there's a natural cardinality that goes into them, and all those things, right?
Right.
In this context, the compositionality of would-be paths or the generalized notion of paths is much more complicated. It's by no means obvious what you should do, right? And if anything, there is a larger set of possibilities, and this relates to something that I've mentioned in other streams for people who are aware of the sort of arity research that I do, is all these compositions of possible ternary edge compositions, right? One way to think of those is to think of generalized paths, right? Because if you imagine one way to think of paths in a graph, right, in the traditional sense, is that you have by, for example, specifying distances, right? you have a direct way to reduce a graph to a binary graph to another binary graph by saying, find all the length 2 paths here. And so that gives you a new graph, which gives a binary link between any pair of nodes that has a length 2 path between them, right? So that compositionality becomes quite straightforward in the path case because there's really only one pattern that you're checking for, which is this length 2 path that you can just iterate. In this context, things become much more sort of multiple and sort of colorful in a way, because you have more patterns that you can use, and the notion of adjacency is just more general. So I'm not sure what this would be like, but in an analogy, I guess you could imagine that this is something like an area function that you're defining. You're assigning a number to something that is defined by 3 points. We know what that is. If we have 2 points and you assign a number, we call that a distance. If you have 3 points and you assign that a number, we call that an area, right?
Right.
In general, right? So that could also be a very simplistic interpretation of this. That this is some kind of area form, in the end.
Right.
Right. But yeah, it's also
yeah. And therefore, that are vector. What were vector fields in the arity2 case become akin to bivector fields or something in the arity3 case?
Exactly.
For instance.
Exactly.
Which that's an interesting intuition.
Yeah. Exactly. Yeah. Something like that, I think. And then this goes for all orders. You can go to higher orders, and you have all kind of a simplicial. I mean, basically, given an unordered hypergraph like this, of an arbitrary order, you have sort of the simplicial hypergraph induced by it, or the simplicial complex, the simplicial cell complex induced by it, which is automatically defined, right? Because you know what in simplicial complex, you know that every time you have an edge, you need to have all the faces and all the sort of cascading, sort of downwards induced faces. So if you think about it in a way, going from undirected graph to a graph, that's kind of like getting the simplicial complex out of the graph, right? It's just a very basic one. In this case, it will be a bit more interesting because you get sort of faces defined as the edges, with an orientation, and then you get the faces of the edges, right? That would be the pairwise connections and so on. So I would say that you end up with something that actually was referred to in this paper that was recommended by Carlo Rovelli and Václav. This guy came to the summer school, and this is, I think, what you naturally have. I mean, all that machinery we can recover here. By the moment you establish a higher order hypergraph, you can always have the sort of downwards simplicial complex induced by it, and so you have all this machinery of discrete simplicial geometry that goes with it, right? But then, of course, there's the ability to do more than just that, and to do sort of definitions that are sort of proper to these hypergraphs and don't use the induced simplicial structure, because the simplicial structure has a lot more information that is not in the original hypergraph, right? So anyway, I think that those are some of the open directions that are interesting to keep in mind.
Absolutely. No. So we should, amongst other things, in the next stream, hopefully we should get to working through exactly these examples, but in the ternary case, to see if we can, spot commonalities and spot places where where the binary constructions kind of break down.
Yeah.
Those will be interesting cases. I agree.
For sure, I agree.
Great. Okay. Yeah. I'm sorry to cut this off, but unfortunately, I do need to run in a few minutes ago.
Yeah. No problem.
So should we say provisionally sometime next week? We don't know exactly when.
Yes. Whenever, as I say, Tuesday just happens to be inconvenient for me, but I think Wednesday same time will be perfectly fine.
Okay. Well, yeah. Maybe let's preliminarily say Wednesday, whatever it is, Wednesday 6 p.m. UTC. But we'll confirm hopefully later on this week.
Yeah, and so for anyone watching, remember to check our social media for that, and as usual, I share our community link where you can find our Discord, and in case you want to join the community and be more in the real-time communications with us. And yeah, it was a pleasure, Jonathan, as usual.
Yeah, likewise. This is really fun. I'm enjoying these.
All right.
All right. Well, thanks everyone for coming, and we'll see you very soon.
See you next week.